Okay, welcome back to 3.2, but this time we're going to be continuing with the mean value theorem, which is another existence theorem. The mean value theorem states that if a function f is continuous on a closed interval ab and differentiable on an open interval ab, then there must exist at least one c value on the open interval ab such that f prime of c is equal to, and here is your question, what would f prime of c actually be equal to? So c has got to be some value in between a and b. That's because the function itself, we'll call this function f, this function itself is continuous on the closed interval between a and b, and it's differentiable on the open interval in between a and b. And there has to be some c value, somewhere's in here someplace. I'm not quite sure where the c value is. Could be closer to a, could be closer to b, could be smack dab in the middle, but there has to be some c value in between a and b such that when I connect these two endpoints, when I connect the point a comma f of a to the point b comma f of b, and you can continue through there if you want and continue to look at it as if it were what kind of a line would this be, connecting two different points on the function? This is called a secant line. So connecting the two endpoints of your closed interval gives us a secant line through the function that has a slope that has to be equal to the slope of the tangent line someplace in between a and b. So think about this. You get this secant line with the slope just about like this, and you're going to follow it up until we're right around here. Somewhere's around here, we're going to have a tangent line such that the tangent line and the secant line are definitely parallel because they have the same exact slope. So the slope of the tangent line has to equal the slope of the secant line. F prime of c represents the slope of the tangent line at some c value. So here's my c. Looks like c happens to be a little bit closer to a, if that's drawn nicely in your perspective. And how are we going to connect these 2 points here and talk about the slope of the secant line? We do that simply by taking the change in the y over the change in the x. So this formula says f of b minus f of a all over b minus a. This is the slope of the tangent line, and this is the slope of the secant line. So I don't think you're going to find this notation in a book anywhere. This is just Talon talking to you. But the slope of the tangent line at c is f prime of c, and the slope of the secant line that connects your two endpoints, a and b, or a f of a and b f of b, will be the slope of the secant line. This also means a little something more in the context of a problem. The slope of the tangent line should represent an instantaneous rate of change of the function at c, whereas the slope of the secant line should represent an average rate of change of the function from a to b, or over the interval ab. So make sure we understand that the slope of the tangent line is giving us an instantaneous rate of change of the function f at x equals c for the function. And this is going to equal not an instantaneous rate of change, but an average rate of change. Of the function f from x equals a to x equals b. Or I suppose I could have said on the interval of ab. Okay, so this in a nutshell is your mean value theorem. Let's recap it, say it one more time. It's kind of like Rolle's theorem, but it's a little bit more open-ended, so to speak. Mean value theorem tells us that if a function is continuous on a closed interval from a to b, and differentiable on the open interval from a to b, then there has to exist at least one c value in between a and b, where f prime of c is equal to f of b minus f of a divided by b minus a. this says the slope of the tangent line has got to equal the slope of the secant line. An instantaneous rate of change for some value c on the closed interval has got to be equal to the average rate of change of the function on the closed interval. All right, let's see how this applies. We're going to do some example problems. Let's erase this. For all of our example problems, we're going to have the same exact set of directions. Those directions are going to say to you to determine whether or not the mean value theorem is applicable to the given function on the given interval, and if so, find the c value guaranteed by that mean value theorem. So, directions. Decide if the mean value theorem applies for the given function and interval. If so, determine the c value I'm going to put an S in parentheses right there because it's possible that you could have more than one c value, guaranteed by the mean value theorem. Okay, so let's go right ahead with example 1. The function I'm going to give you is x squared plus 4x minus 3, and the interval, the closed interval, is going to go from -2 to 5. So we need to ask ourselves 2 questions. Number 1, is this function f of x continuous on the closed interval? So is f continuous on the closed interval from a to b, which in this case is -2 to 5, question mark. This is my question, this is my thought process, and I'm looking at the function. The function is a nice simple quadratic. Because it's a quadratic, it's automatically a polynomial function. We know that polynomial functions are nice friendly functions. They're everywhere continuous, everywhere differentiable. So therefore, would f of x be continuous on the closed interval between -2 and 5? Yes. I'm going to put a bullet here and I'm going to say f is continuous on the closed interval between -2 and 5. After I check continuity on my closed interval, it's my job to now ask, is f differentiable on the open interval between -2 and 5? And that is the question. Again, I'm asking myself, this is my bubble thought process here, but I am asking, is f differentiable? You might have heard me just state that f of x happens to be a polynomial function, everywhere continuous, everywhere differentiable in the set of real numbers. So of course it's going to be differentiable on any interval you pick. So f is differentiable on the open interval between 2 and 5. You should answer both of these questions. It should be clear that you understand the premise of the mean value theorem. These 2 things must be true in order for you to continue. So I'm going to say yes. The mean value theorem applies. Or is applicable. This is part of my answer, and I expect it to be part of your answer if you're asked to tell one way or the other. Now we have to find those c values. Okay, so we're going to find c such that f prime of c is equal to f of b minus f of a all over b minus a. Well, pretty simple. I have my original function, f of x equals x squared plus 4x minus 3. We're going to take the derivative of that function, which is going to end up giving us 2x plus 4. And we're going to put that down for f prime of c. Now I know it says f prime of c, and when I'm finished here, I'll have an x value, and then I'll just say c is equal to whatever the x value happens to be. So f of b, what's my b? I have an a-b interval right here, so my b is 5. This is f of 5 minus f of negative 2 all over 5 minus negative 2. Not much I can do with that 2x plus 4 right now until I get some kind of a number over here. F of 5. Now I can take this 5, bring it back over here. Just in my mind, I really don't have to see this work for anything. 5 squared is 25, plus 4 times 5 is 20. So 25 plus 20 is 45. Take away 3. 45 take away 3 would be 42. So f of 5 is 42 minus, now I don't want f of 5 anymore, I want f of negative 2. So let's do a little bit more of this work in our heads. What's negative 2 when I square it? Should be positive 4. Plus 4 times negative 2 gives me negative 8, and then minus 3. 4 minus 8 is negative 4. Minus 3 more gives me negative 7. And 5 minus the negative 2 becomes 5 plus 2, which is 7 itself. Let's see, save a little space here. 42 plus 7 gives me 49. Divided by 7 is 7. So I have a 2x plus 4 equals 7. Subtract 4 from both sides of the equation. I get 2x equals 3. Divide both sides by 2, and I have x equals 3 halves. If you'd like, you may call that 1.5. And I think that that's going to be my c value. I just need to make a double check here and make sure that this 1.5 or this 3 over 2 does indeed fall in the closed interval that I was given. Now is 1.5 somewhere between negative 2 and positive 5? Yes, indeed, it does check. So my c value is 1.5. And these two box things are my answers up on the board. So I have applied the mean value theorem, and I have found that c value that is indicated that I can find. Now, if I were to draw you a picture of this, we would have a quadratic. The quadratic would obviously open up. The points that I'm playing with, however, that negative 2 paired up with negative 7, so that's kind of low, not a big deal. But this 5 comma 42, I'm not interested in graphing 5 comma 42, so I'm going to leave this picture off the board for now. You can, however, punch this into your graphing calculator, take a look at what the quadratic looks like, maybe even connect in your mind between the negative 2, negative 7, and the 5, 42, and you can see that very steep slope of a 7. And then the original function would have a slope of 7 only at 1.5. All right, so we're going to let this go, and we're going to move on to example number 2. So I'm going to give you a different closed interval and a different function, and we'll go through this thing and see what happens again. So example 2. My function this time is going to be given as 1/2 x cubed, and we are going to be on the closed interval between 1 and 4. All right, first thought process. Now I don't have to write the bubbles up there, I hope, but I should be asking myself, and you should be asking yourself, is this function continuous on the closed interval between 1 and 4? We're looking at the function. The function is a cubic function, which means it's a polynomial function, which means it's a nice friendly function. It's everywhere continuous and everywhere differentiable. We need to, however, make a statement that says, yes, f is continuous on the closed interval of 1, 4. Wouldn't really matter what the interval is. I can say that the function is going to be continuous anywhere. And f is differentiable on the open interval between 1 and 4. So, therefore, yes, the mean value theorem applies. A little crazy on my little lesson. Now we're going to find the c value in between 1 and 4, open interval, not closed interval, such that f prime of c is equal to f of b minus f of a divided by b minus minus a. This is the change in the y values over the change in the x values, which represents the slope of the secant line. This is the slope of the tangent line. So I'm looking for my first derivative. I come over here, I see my function, it's 1/2 x cubed. I can take that derivative relatively easily, just need to bring that 3 down. This gives me 3/2 x squared is equal to f of 4 minus f of 1 all over 4 minus 1. Now let's take that 4 and put it in here. What is f of 4? 4 cubed is 64, half of 64 is 32. So I have a 32 right there. F of 1, I'm going to take a 1 and cube it. When I take 1 and cube it, I get a 1, multiply by a half, it brings me back to a half. So I have 32 minus a half all over 3. You should know me well enough that I'm going to multiply through and get rid of this half sitting here. So I'm going to multiply all my terms in this fraction by 2. It's going to give me 64 minus 1 all over 6. I haven't changed the left side of the equation. It still remains the same. This is 3/2 x squared is equal to 64 minus 1 gives me 63 over 6. And I think I will multiply by 2 over 3. Multiply by 2 over 3. X squared ends up equaling, let's see, 2 goes into itself once and 2 goes into 6 3 times. 3 goes into 63 21 times, and 3 goes into 21 7 times. This gives me x equals plus or minus the square root of 7. So I think my c values are going to be positive or negative square root of 7. I have 2 answers here. I have x equals positive root 7, and I have x equals negative root 7. But I need that root 7 to fall in the open interval between 1 and 4. And I don't think the negative value is going to do that. So therefore my c value, I'm going to take the positive answer, and I get c equals the square root of 7. Kind of a strange thing, but not impossible. So you can again grab your graphing calculator, take a look at the function f of x equals 1/2 x cubed on the interval between 1 and 4. Imagine a secant line connecting those, and then imagine that you can square root of 7 is somewhere in between where 2 and 3. Somewhere in there, you're going to find the slope of a tangent line equaling the same thing. Okay. Let's move on to a third example. Again, I haven't been graphing anything for you. It's just a matter of grinding this stuff out. I can pretty much leave that there, can I? Maybe not. Maybe not. Maybe. Maybe not. Example 3. My function is f of x equals -1 plus the absolute value of 2x minus 6. And the interval I'm on is 1 to 4. Looks a little familiar for my interval. So -1 plus or minus the absolute value of 2x minus 6 on the interval between 1 and 4. Now hopefully you understand that anytime you're given an absolute value problem, you should try and graph this thing and decide your answer from the graph of the function as opposed to trying to take a derivative or doing anything funky with your absolute value. So in order to graph this, I like to rewrite it. I'd like to take my 2x minus 6 and put it first, and take my minus 1 and put it later on, because this -1 serves for me as being a vertical shift down 1. I also would like that 2 off the x value so that I can read my horizontal shift. I can only read a horizontal shift when it's applied directly to x, not 2x. So even though some of you might think that this means a shift to the right by 6, that's not true. You have to be only affecting the x. This is definitely a shift to the right by 3, and this is definitely a shift down by 1. This is my f of x equals. Okay, I am going to have a slope of 2 on one side of my vertex and a -2 on the other side. You might want to factor this 2 out, or you can leave it where it is. Either way, the 2 represents either a vertical stretch or a horizontal shrink, but it's going to make your absolute value function look a lot skinnier than the normal absolute value function. So let's take a peek on the interval between 1 and 4. The absolute value of x looks like that in quadrants 1 and 2. Now I need to shift it to the right 3 and then down 1. Shift my vertex, shift the whole thing to the right 3, 1, 2, 3, down 1. This gives me a new vertex at 3, -1. It also tells me with this 2 right here that from the vertex I need to go up 2, right 1, up 2, right 1, up 2, right 1. So I'm going to go up 2, right 1, up 2, right 1, up 2, right 1. And on the left side, I'll go up 2, left 1, up 2, left 1, up 2, left 1. And this becomes f of x equals the absolute value of 2x minus 6, quantity minus 1. I think what I'm going to do is just pick a point here. I'm going to pick 3, -1 first. 2 times 3 is 6, minus 6 is 0. Absolute value of 0 is 0. Take away 1, you get -1. So yes, that point is definitely on my graph. I think I'll label this one. I went up, how many? I went up 2, right 1. So if I went up 2, right 1, that should be the point 4, 1. Let's just check 4, 1. 2 times 4 is 8, minus 6 is 2, absolute value of 2 is 2, minus 1 gives me 1. I think I'll check a point over here someplace, maybe my y-intercept. This is 0, comma, let's see, I went up 2, I went up 2, I went up 2, so I've gone up 6 from -1, puts me at 5. Let's go ahead and put a 0 in here. 2 times 0 is 0, minus 6 is -6. The absolute value of -6 is 6. Minus 1 gives me a 5. So I'm pretty sure that I've graphed this function correctly. Now I want my interval to be in between 1 and 4. So here's 1, 1, comma, 3, and here's 4, 4, comma, 1. So I can pretty much just throw away everything else on the graph that's not in between -1, 3, and 4, comma, 1. So, first question, now that I understand what the function looks like and what it means, I need to check to see whether f is actually continuous on the closed interval between +1 and +4. And yes, indeed, it looks like I could draw this thing, trace it without picking up my pencil. So f is continuous on the closed interval from 1 to 4. My next question is to ask myself, is the function f differentiable on every single point between 1, 3 and 4, 1? And the answer to that had better be a no. We don't have differentiability at a cusp, so f is not differentiable on the open interval between 1 and 4. And I want you to tell me why. I want you to tell me that f prime of 3 is not defined. Okay, and 1 is less than 3 is less than 4, which tells me 3 is in the middle someplace between 1 and 4. So no, f prime is not defined at 3. So my answer to the question is no. The mean value theorem does not apply. If the mean value theorem does not apply, I don't need to go looking for my C value anywhere, because I'm not guaranteed to find one. Only if I'm guaranteed to find at least one C should I go looking for it. So there's example 3. I have 2 more examples for you. I think I have 2 more examples for you. Check my notes on that one. Here is example 4. F of x is equal to x squared minus 2x minus 3 over x plus 2. And then I would like to talk about the interval between -1 and 3. So, 2 questions have to be answered. I need to know if the function is going to be continuous on the closed interval. I also need to know if the function is going to be differentiable on the open interval. So let's take a peek at our function. I see it's a rational function, so that means that I might have a little bit of problems in some places. Let's see what's going on. One of the first things I notice at the is that the function is top heavy by exactly 1. And if you recall from pre-calc, that means that you're going to have a slant asymptote in this function. No horizontal asymptote because we are top heavy. I also noticed that we have a denominator of x plus 2, and this number right here that's going to make my denominator equals 0 would be a negative 2. So my question is, at negative 2, would this function be a 0 or 0 or undefined, or do I even care? Looks like negative 2 doesn't happen to be in my interval between negative 1 and 3. So it's a little bit of a pain to try and figure that out. So, let's see. F is, just write some little brainstorm ideas down here before I answer the question. F is undefined at x equals negative 2. I'm not sure if it's a whole or not, but if it is a whole, maybe I could rewrite this function and do a little something more. Is negative 2 the only place where the function f is undefined? I think it's going to be, because we don't have any square roots. The only thing that's going to make it undefined would be a 0 in the denominator. Whether it's a 0 in the denominator and the numerator, it doesn't really matter whether I have a whole or an asymptote.
Shalom, Easy, please report to the main office. Shalom, Easy, please report to the main office. Thank you.
So if the only point that where my function is undefined is at negative 2, then I can go ahead and say that f has to be continuous on the closed interval between negative 1 and 3. Now, the question is f going to be differentiable everywhere between a negative 1 and a 3? It's a good question. I don't think I'm going to have any cusps. I'm not looking at any absolute value functions for cusp or anything else. I'm also looking at taking this derivative, and I know that when I do take the derivative, I do low to high minus high to low all over low, low. The only denominator I'm going to get is the one that I already have. So I know that f won't be differentiable at x equals negative 2, but what do I care if it's not in my interval anyway? So I'm going to go ahead and say here that f is differentiable on the open interval between negative 1 and 3. Alrighty. I mentioned that we had a slant asymptote. We don't necessarily have to go ahead and find any slant asymptote unless you'd like to look at the picture, and maybe we should, just to get the idea down a little bit better for us, but I think I'll let that go for right now. I need to answer the question though, is the mean value theorem applicable? And the answer to the question is yes. The mean value theorem applies. It applies to this particular function on this particular interval. So now we need to find that c value. We need to find that c value on the open interval between negative 1 and 3 such that f prime of c is equal to f of b minus f of a all over b minus a. Or in other words, the slope of the tangent line has to equal the slope of the secant line. So you mean I have to take this derivative, huh? I didn't want to have to take the derivative. I can take it. We can do low to high minus high to low all over low, low, or we could actually do a synthetic division or a long division and break the function down. I doubt highly that most of you would do that, so I'm going to go ahead and use my quotient rule. So the first derivative, the bottom, x plus 2, times the derivative of the top, 2x minus 2, minus the top, x squared minus 2x, minus 3, times the derivative of the bottom, which is just a 1, all over the bottom, x plus 2, quantity squared. And we're going to make this nice by simplifying it out a little bit. We're looking at 2x squared minus 2x plus 4x minus 4. And I'll distribute this negative as I go through. Minus x squared, positive 2x, positive 3, all over x plus 2, quantity squared. I have a 2x squared minus an x squared, which gives me 1x squared. I have a negative 2x and a positive 4x, giving me 2x, plus another 2x, bringing me back to 4x, or if you prefer, those are opposites, and all I have left is the 4x for x terms. And negative 4 plus 3 should give me a negative 1. Just make sure everything looks okay. Sounds good. And we're going to divide this by x plus 2 quantity squared. All right, let's see what it's supposed to equal. What's f of b? What's f of b? What's my b? My b is a 3. F of -1 all over 3 minus -1. That's definitely a 4 on the bottom because when you subtract a negative, it means add. 3 and 1 is 4. F of 3. I need to come over here and think about what is f of 3. I have 3 squared minus 2 times 3 minus 3 all over 3 plus 2. So this is 9 minus 6 minus 3 all over 5. 9 minus 6 minus 3, I do believe that's going to give me a 0, and 0 over 5 is 0. So I now know f of 3 is 0. I now want f of -1, so that's -1 squared minus 2.
Mr. Thompson and Ms. Finch, please report to the guidance office. Mr. Thompson and Ms. Finch, please report to the guidance office. Thank you.
I square -1, I get 1. This gives me plus 2, and then minus 3. Oh, I see another 0 coming. All over 1. This is 0 over 1, which is 0 again. Well, at least it makes life easy for us, doesn't it? So I have 0 divided by 4, which is 0. And anytime I have a fraction on one side of the equation and a whole number on the other side, I simply make a fraction on the other side of the equation with my whole number and I cross multiply. This gives me x squared plus 4x minus 1 has to equal 0. So now I'm looking for those x values. This doesn't look like I'm going to get a very nice factored form out of this because there's only one way to make a 1 and I'm nowhere near that 4 with it. So I have to go about using my quadratic formula. So I'm looking at x equals -b, I'll write the quadratic formula out for you, plus and minus the square root of b squared minus 4ac all over 2a. So if my b is 4, my negative b is -4, plus or minus the square root of b squared is 16 minus 4ac. My a is a 1, my c is a -1, so ac is -1 all over 2 times 1 for my a. This gives me -4 plus or minus the square root of 16 plus 4 is 20 all over 2. -4 over 2 plus or minus the square root of 20 can be broken down into 4 times 5 inside here. So 2 root 5 all over 2. -4 divided by 2 is -2 plus or minus the square root of 5. This is 2 answers. X equals -2 plus the square root of 5, and also x equals -2 minus the square root of 5. So you pop those things on your calculator if you need to, and I don't have my decimal approximations here. I'll tell you what, I do know that the square root of 5 is a little bit more than 2 point something. So if I take -2 and I subtract 2 point something more, I'm going to be -4 point something. So I don't want this. This is not in my interval. This is not in the interval between not in -1 and 4. However, if I take a -2 and I add 2 point something to it, I'm going to be positive by just a little bit. So this answer is definitely within my interval. So I'm going to say that this is my C value, and I'm going to box that just like this. This is the square root of 5 right here. And of course, if you did pop it in your graphic calculator or any calculator at all, you would find that the C value is in between a -1 and a 3. And I think we are good with our answers there. All right, last and final example, and hopefully it's going to go a little bit faster. However, I know you're not going to like it because we are dealing with a little bit of trigonometry. Want to throw a trig question on there for you. And let's see how we do. So I have f of x is equal to cosine x on the closed interval between 0 and pi. The cosine function, you should know it, it's nice and smooth and friendly function, so it's everywhere continuous, everywhere differentiable. We just need to state it, okay? F is continuous on the closed interval between 0 and pi, and we also need to state that f is differentiable on the closed interval, on the open interval between 0 and pi. Okay. That being said, yes, the mean value theorem applies. Okay. So now that the mean value theorem applies, we need to find out what C value is guaranteed by the mean value theorem that falls in this interval. We're going to have at least one. We might have more than one, but there's going to be at least one. So now we need to find C such that, or I should say C on the open interval between 0 and pi, such that f prime of C is equal to the slope of the secant line, f of b minus f of a all over b minus a. I'm doing the same thing over and over. I set up my formula over and over. And I also sometimes tell myself I'm doing the slope of the tangent line being equal to the slope of the secant line. That's the main idea behind the mean value theorem. So I need the first derivative. What is the first derivative of cosine x? And you should be able to tell me that the first derivative of cosine x is negative sine x. F of pi minus f of 0 all over pi minus 0. So f of pi, I need to come back over here and I actually need cosine of pi. Two different ways I would hope you do that. One would be on your unit circle. Here's pi right over here. The cosine value is the first coordinate, which is negative 1, 0. So cosine of pi is negative 1. Another way I would hope you would do that would be to look at the cosine function. Cosine starts high, ends high, between 0 and 2 pi. Halfway in the middle, it hits a low. Halfway between its high and low, it hits a 0. Halfway between its low and high, it hits a 0. And the cosine function is a nice, smooth, continuous, everywhere differentiable function. I want the cosine of pi. Here's pi. And right down here, I have pi, comma, negative 1. So once again, the cosine of pi is negative 1. So f of pi would be, I think I'll just write cosine of pi minus cosine of 0. And so that's negative 1. Minus, what's the cosine of 0? I can get that right here. This is 0, comma 1. I can also get that right here. This is 1, comma 0. Either way, you should be looking at the cosine value being the first coordinate on your unit circle or the height of your function. Okay, so cosine of 0 is 1 all over pi. And this is negative sine x. So I have the negative sine of x is equal to negative 2 over pi, which is really kind of a weird thing to figure out. I'm going to multiply both sides by negative 1 or divide both sides by negative 1, whatever you want, but we're going to come up with a positive 2 over pi. 2 over pi is not the answer to the sine function for anything I know of, so this has to be a calculator-dependent question. You must resort to your calculator at this point, and the x value, or let's just back this up a second, 2 over pi, I don't know exactly what value this is. It's approximately 2 divided by 3.1415, blah, 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 blah. So it's not quite a whole. I'm not quite sure what it is, but I can tell you where the sine function is positive. The sine function is going to be positive either in quadrant 1 or in quadrant 2. So in quadrant 1, you're going to have a reference triangle with a reference angle alpha. And in quadrant 2, you'll have a reference triangle with a reference angle alpha. These alphas will be the same because they're stemming both from the same input in your calculator. This will be my angle measurement here. That will be my angle measurement there. So let's find this. You pop this in your calculator by saying alpha equals inverse sine of 2 divided by pi. And that is going to show up in your calculator as being approximately 0.6901070914. This tells you this angle measurement right here. Now let's not forget that everything in calculus is done with the units of measurement for angles as radians. So this is approximately 0.690 radians right here. So this is going to be my angle measurement. In quadrant 1, your reference angle is your angle itself, so I can just say x in this case. X is my angle, not theta. They didn't give me a theta. They didn't give me an alpha. I introduced the alpha because I knew I needed a reference angle. So this is approximately 0.690. I can't leave it off, even though it doesn't round up. I need to be accurate to at least 3 decimal places. So let's just be safe and put 0.1 radians. I'll go 4 decimal places. X over here is going to equal pi, take away that alpha, because this is pi all the way halfway around your circle is pi radians. I need to subtract alpha radians. So this is going to end up equaling pi in your calculator is approximately 3.1415, take away 0.6901, and I know you're not used to it, but it's 2.451485562 radians. So I have 2 answer choices that could possibly be my C. However, let's see where my interval is. My interval is between 0 and pi. Pi is approximately 3.14. I know that 0.6901 is in between 0 and 3.14. I also know that 2.451 is in between 0 and 3.14. So it looks like I've found 2 C values. C could equal 0.6901 radians, or it's possible that C could equal, we won't say equal, we'll say approximately, because we are rounding, 2.451. I could stop there. I'm going to throw the 4 on it. I'm not going to bother rounding at all. And I'm going to say that those are my 2 C values guaranteed by the mean value theorem. And both of them happen to fall within my interval. It's possible that one would and one wouldn't, but in this case, they both did. It's about all we have for mean value theorem. Before I close, I want to talk to you about how the mean value theorem and Rolle's theorem connect with each other. And I'm just going to pick a really nice function, something that like nice quadratic function going up like this. I'll erase this tidbit of information that's in the middle. Rolle's theorem says that if I have two points on my graph, the function f, such that f of a is equal to f of b, in other words, they're at the same exact height, then we're guaranteed to find some tangent line that has a slope of 0. What if I make that point go a little higher or a little lower? If my slope here is not a 0, but it's something else, I'll do this up here. What if I have my A here, and what if my B is up here? And I connect from A to B. I don't have a 0 slope, but I'm still guaranteed to find a C value down here someplace, such that the slope of the secant line has to be equal to the slope of the tangent line. And that means that those values would be parallel. So if I tilt this down, I bring my B value down, I end up having a slope of 0. Slope of 0 matches a tangent line with a slope of 0. This is Rolle's theorem. And this is the mean value theorem. So in my world, I think that Rolle's theorem is one particular example of the mean value theorem. And I remember Rolle's theorem being the one that has a slope equal to 0 for both its secant line and its tangent line because of the O in Rolle's. To me, that O in Rolle's kind of looks like a 0, and it connects that. And the Rolle's theorem is the one that deals with the 0 slope, both on the secant line and the tangent line. Whereas mean value theorem, you don't have to have a slope of 0. Your slope could be anything on your secant line. You're guaranteed to have some tangent line with the same slope as long as the function is continuous on the closed interval and differentiable on the open interval. Always check continuity first, then differentiability. You shouldn't be telling me that a function is not differentiable at x equals 5 if it wasn't even continuous at x equals 5. So deal with continuity first, differentiability second, and then if Rolle's theorem or the mean value theorem apply, go ahead and find your C value. Remember Rolle's theorem, f of A has to equal f of B. We don't have to do that here. Alrighty? Have a good day. Do your homework.